Okay, so now we're gonna go back to that example we did in the last video about adding a day onto our board games and card games. Again, a family's playing games. On Monday, they're gonna roll a tetrahedral die, a four-sided die, decide if they're gonna play a board game or a card game. They're gonna do it on Tuesday, they're gonna do it on Wednesday. Okay, so you're gonna see a bunch of numbers here. This is where this comes from. Okay, so a board game is 3/4, right? But you'll notice in a board game they have 0.75. If you were to go 3 divided by 4, you get 0.75. Card game only happens if you roll a 1. So that's 1/4. You know, four-sided die. If you get a 1, that's only 1 out of 4 chance. And if you go 1 divided by 4, you get 0.25. So when you look here, remember when we're doing probabilities, B, 0.75, that's where it's coming. The probability of rolling a board game, 0.75. The probability of rolling a 1 and getting a card game is 0.25. So you can see that we've already gone through and matched up all these things on your notes. There you go. Saved you some time. So if we want to find the probability, these are not equally likely. You can't just say, oh, well, there's 8 choices. I want this one. That's 1 out of 8. Because it's not. Because they're not all equally likely to happen. So what you have to do is inside the tree diagram, we multiply. Here's what I mean. Board game, board game, board game. 0.75, 0.75, 0.75. Multiply them together. That's what those parentheses mean. You multiply 0.75 times 0.75 times 0.75, you get 0.421875. Okay, so let's do that with all of these. Board game, card game. Follow your tree. 0.75, 0.75 times 0.75. Sorry, and I'm going to rush here and get sloppy. I will do my best not to. But I'm going to anyway. Times C. Now the C is the 0.25. There's only 1 out of 4 chance. 0.25. You type all of that into a calculator. This times this times this. And you get 0.140625. Okay? So now, BCB, we're going to do the same thing. 0.75 times the C, 0.25, times C, 0.25. And if you kind of get the idea, you can go ahead and do it and then just make sure your answers match up with mine or make sure that mine are correct. You're going to see here we have two 0.25s here. Nope, this should be a 0.75. See? That's why you got to make sure your answers, or my answers, match up with yours. B is 0.75. Okay? And since that's kind of the same as the other one, 0.140625. All right, BCC. So it's going to be 0.75 times 0.25 times 0.25. BCC. You type that in, being careful here, 0.046875. CBB, 0.25 times 0.75 times 0.75. Told you, getting sloppy. We get, again, 0.140625. Thankfully, this one is done for us. Okay, so if we had C, B, C, it's 0.046875. 0.25 times 0.25 times 0.75. Okay, that'll give us 0.046875. Again, a lot of these are going to be the same. This one's different though. 0.25 times 0.25 times 0.25. 0.015625. All right. Well, good news. We've already done number 4, right? We figured out the probabilities. So now, what is the probability there will be exactly 2 nights? Exactly 2 nights. So let's look at all of our outcomes that have exactly 2 nights. Right here, BBC. Ooh, I want to still be able to see it here. Oops, sorry. Maybe I can do this. Okay, then this one, BCB. This one, CBB. And I think that's it. All right, so inside the tree diagram to figure out probabilities, we multiply. But when we're doing things over, like we're talking about more than one outcome, we add them together. So here's what this means. This BBC, okay, that is 0.140625 plus, let me put that in a different color, BCB, 0.140625 plus, for multiple outcomes here, right? CBB, which is, well, the same thing, isn't it? And when you add all of those together in my different colors here, we get 0.421875. Okay, so about a 42% chance that you're going to have exactly 2 nights of board games. So what is the probability that you're going to play at least, we've talked about that before, 1 night of card games? If you're going to play at least 1 night of card games, the only time you're not going to play any card games is if you had board game, board game, board game. Every other one of these, you're going to play a card game. Might be more than one, but it just says at least one. So remember, if you add all these up, they're going to add to 100%. So if we want to figure out what the probability is that we're going to play at least a card game, there's only one chance that it doesn't. So we go 1 minus this, nope, this probability right here, okay? So 0.421875. So the probability you're going to play at least 1 night of card games is 5.578125. Okay, about 58%. Okay, all right, we're going to quickly move on to the next example here. Because in this one, we're going to have 3 children being born. Okay, I think we've done one before where we had 2 children being born, so now we're going to do 3. So let's quickly set up the one where we did 2 children. Getting started is hard. 3 children. No twins or triplets. B for boy, G for girl. Consider the first birth to be the first stage. So our first kid is either going to be a boy or a girl. Our second kid, guess what, is going to be a boy or a girl. So if I have a boy the first time, boy or girl. If I have a girl the first time, boy or girl. Third kid, guess what? Boy, boy. You can have another boy, or you can have a girl. Boy, girl. Boy, girl. Boy, girl. Okay, probably not the neatest. All right, but you can see that we can have 3 boys, boy, boy, girl, boy, girl, boy, and so you don't have to try to figure these out. You can just follow along the branches of the tree. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Girl, girl, girl. Okay. Oh, I missed this one. Sorry. I erased my G and never put it back. Okay, so now it says write the probability of each stage outcome in the tree diagram and determine the probabilities. Again, I'll try to go through this pretty quick, so if you need to pause it, go ahead. It's a probability that you're going to have a boy. 50%, right? 0.5. What's the probability you're going to have a girl? 0.5. And that, in this case, is going to be the same for all of these. So really, once we figure it out, we'll be able to know all of them. Because in this case, it's the same. Okay, so for boy, 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 it's going to be 0.5 times 0.5 times 0.5. If you type that into a calculator, you get 0.125. These are equally likely, so you kind of do that 1 out of 8 thing. 0.5 times 0.5 times 0.5. They're all going to be the same all the way down, right? So let's save our time. We know they're going to be the same, okay? So what is the probability of having 3 girls in the situation? Is that more or less than having probability of having exactly 2 girls and 3 boys? Okay, 3 girls. G, G, G. The probability of that is right here, right? 0.125, because they're all the same. Remember, now if we're talking about multiple outcomes, exactly 2 girls, if I looked on my list here, this one, B, G, G, which is 0.125, G, B, G, this is a G here, sorry, 0.125, and GGB, because it says exactly. When we're talking about multiple outcomes, what do? Okay, within the tree diagram, we multiply to figure out the probability. When we're talking about more than one outcomes, though, we add them together. So, is this less than or greater than? Okay, this is going to be less than. Okay. Your chance of you having 3 girls is less than your chance of having exactly 2 girls. Okay. Now look at the next one, the last one, right? Look at the word at least 1 girl. What is the probability that they're going to have at least 1 girl? The only chance that you have that you don't have at least 1 girl is right there. Boy, boy, boy. Everything else has a G in it. So remember, instead of, you could add all of these up. You could add up 0.125 7 times, or we could say, you know what? I know they all have to add to 100% or 1. I can just subtract off the one that doesn't have any girls. 0.125. Oh, let's not finish sloppy, right? So the chance that you have at least 1 girl, right? This is like saying 1 minus boy, 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 is 0.875. If you wanted to make that into a percent, it'd be 87.5, 87.5, or approximately 88%. Okay? Take what we've been doing with tree diagrams, take what we've been doing with probabilities, okay? And we're just adding another event on. So that's why this is calculating probabilities of compound events.